Hey, good morning, everybody. I know it's just before lunch, but hopefully this will be an interesting topic. I'm Paul Artman from AMD. We've got Dirk Blevins from Intel, and we've got Nance from Jabil, and we're going to kind of walk through a little bit of history of DC-MHS and then what we're doing next. So what is DC-MHS? So what I would start with is as an industry, we did a lot of custom designs. I've traditionally worked at a lot of OEMs, and a good example is OCP. So for a long period of time, everybody had a custom network card. And then about 7 years ago, OCP went in and we did OCP Network 3. And it became kind of the industry standard at how to do a network card. And then after that, we did DCSM. So that's a similar kind of industry way around BMC. As we're kind of looking at these Lego blocks, we started with OCP NIC and now DCSEM, we're looking at larger components and how we leverage it. So today, what you generally see is, let me stand for the mic. What you generally see is most vendors have a custom CPU motherboard and multiple ones within a vendor. And that works pretty well. But as you start scaling out and you add Ampere, AMD, NVIDIA, all these different architectures, it's really hard to scale these custom boards. So the idea is that we'd have what we call a host processor module, and it's just basically a building block, a Lego, that's common against the industry. So I can leverage it between my systems, if I'm like a Dell or Lenovo, or across vendors. So I can, the same board could be used by Meta and for Google or Dell. So the idea is really this leverage that we started the OCP NIC. And then the idea is that we use it across multiple segments. So the same motherboard could be used for Edge, it could be used for HPC, and so it's really getting that leverage today. And the issue you get into is every time you do custom boards, it's a lot of design cycles and it's a lot of validation. And so at the end of the day, there's not a lot of value by doing that. And so if you talk about the elements beyond DCMHS, so there's the HPM, which is the major block, that's the CPU. And then within that, we got MPIC, which is the connector type, and that's actually getting really broadly adopted. XIO PESTI, which is the communication. The CRPS, and the CPRS I think is really good. Intel forever had a common redundant power supply. It was kind of Intel unique. They contributed that IP, so we have a kind of next generation power supply that we use across multiple vendors. And then MSIF, which is newer work stream that's starting off around shared infrastructure, which Dirk will talk to. So kind of where we are on, we have a bunch of specs that we worked on. In terms of the HPM, we have the full length width, which looks like a traditional server design with direct plug power supplies. We have density optimized, and these are a little bit more dense and more what you would see with a smaller form factor that's density optimized. And then we have what we're looking at next HPM. So let me kind of go to the next slide here. So what we did is in September of last year, we released 6 specifications to the industry. This included the MCRPS, the HPMs. And what we're looking forward is HPM next. So the first revision of the HPM was really centered around a 19-inch rack and really around enterprise. And as we look forward, we're doing an HPM that's more around an ORV3. And then we're also adding the idea of a 48-volt system, which is becoming more common. ORV3 is 48 volts. We're seeing a lot of accelerators being 48 volts. And then we're adding MSIF on top of that. So we released the spec last September, and now we're working on revisions of HPM next that will come out. And so as you look at HPM, initially it was really optimized around 19-inch. And we said, that's great, but we see a lot of people using the Open Compute rack. How do we do better there? It adds what the OCP rack is, gives you additional width, and it gives you that bus bar. So we're looking at a couple new form factors in that space. We're looking at a full width and a half width, and with those permutations of depths. So those things that are still being worked. But the goal is to have these common form factors that be used across the industry. And really what we're looking is for feedback from the community as this goes forward. We started 2 months ago. So this is kind of a closed group today, but we're similar to the DCSM, there's an open update into the broader community, and we're looking for feedback.
I think the public meeting was yesterday, right?
Yeah, it was yesterday, yeah.
So that's your opportunity to provide feedback. We provide various updates on what's going on, and contact us directly too. We're pretty approachable.
Yeah.
Except for CMAC. It's a joke.
Yeah, we are very open. There's of course, an email where we can get updates on, and really look for the broad participation as this moves forward. It is fairly new. I don't think everybody knows about what we did and released it last year, but we are looking as continue to evolve the spec going forward. And then here's some links to where you can find material. And let me, I'll give it to Rob to go forward.
All right, thanks, Paul. So, one of my primary responsibilities as Director of Technology for Jabil Cloud Business is that I own the product strategy. So being we're a large contract manufacturer, so not only do we have the product roadmap and products that we're building for Jabil branded products that we sell directly to customers, but we're also building boards and systems for partners in the industry that are also in the cloud space. So I was excited when I saw the DC-MHS project start up because this is going to give us building blocks that we can build that will not only go into our products, but will also be able to go into and be leveraged into any work that we do for partners in the industry. This has not really been the case in the past. We've tried to do this, but really it's been, whenever we do work for partners, it's been custom work that is not leveraged from our existing products. So this is one of the big, from my perspective, being where I am at Jabil, but I think even, pretty much everyone in the industry involved in cloud, this should be one of the big advantages that we see is having common building blocks that the industry can use to put together systems for this space. So that's kind of my intro. One of the things I wanted to do is we have a system that we're launching later this year that is going to be MHS compliant, and I wanted to talk through some of the trade-offs and things that we've worked through as we've done this development. So a couple of things that I gave as directives to the team when I kind of redirected us to MHS and said this is something we want to adopt, is I said I want to make sure that we get chassis leverage between our single socket and dual socket systems. This is something that we haven't really had in the past. For whatever reason, and there's been a lot of reasons, we've had pretty much new chassis and different chassis every time we turn around, it seems. So I wanted to make sure we had chassis leverage. And then for sure on the building block side, I didn't want the building blocks that we built to be only for the current generation. I wanted to make sure that they not only leveraged across products within this generation, but could be leveraged generation over generation. Now, luckily, the way that the specifications are written, we kind of get this for free. So if we design to the specifications, we're getting building blocks that will be compatible with future designs. So that's one of the nice kind of free things that we get. This is a high-level architecture picture of how we're looking to develop our single socket with Dino. We started with Dino Type 2. This is the layout of the architecture that we'll have later this year, as well as the FLW two-socket boards that we will have in our next generations. One thing you'll notice here is that we chose to have power supplies on both sides for both of these implementations. This is a little bit different. It's allowed by the spec, but if you look at most of the examples of single socket or Dino designs, you'll see power supplies on one side. There was a couple of reasons that we did this. One was my directive to say that the chassis should be leveraged, and so this does get us chassis leverage between single socket and dual socket. The only thing we really change here is we have a rear wall change for I/O, of course, but really this chassis is like 95+% the same between these two designs. And secondly, we do have customers that like this configuration because of the way they do power distribution at the rack level. And so they say, hey, we prefer to have power supplies on both sides for any of our servers that we deploy. So those are reasons that we did this. However, as we've gotten farther into this and we're starting to look at cost and true leverage and those kind of things, there are a couple of things here that we're sort of reevaluating. We knew there would be extra cost in having the power supplies on both sides for for a single socket Dino board because of the complexity in the power distribution. We have 2 PDBs versus 1. Our fan board's also involved in current sharing and power distribution, but the cost is higher than I thought it was going to be, at least currently, and so that's unexpected. And the other thing is we share almost no building blocks between the single socket and dual socket because of this, other than the chassis. So we do have, OCP board, the OCP MES card, the DCSEM, our storage mid-planes, those are the same. Not that we can get a ton of leverage, no matter what we do here between single and dual, but we could at least have the same fan board if we were to move the power supplies on one side for the Dino board, and we could reduce costs. So that is something that we are investigating for our next generation, or for a change here in how we're doing things. Another area that we have been focused on a lot is the DCSEM to HPM interface. If we obviously before we embraced the DCMHS, we had a BMC down on the motherboard. We did not have a DCSEM. So we had a single FPGA that implemented hardware root of trust and did some other things for our motherboard. This is the architecture that we chose for the current design that we're working on. We chose to have hardware root of trust separate from our LTPI interface for a couple of reasons, but I wanted flexibility in hardware root of trust and wanted to separate that out from LTPI. That obviously has created 3 FPGAs where we used to have 1. So especially nowadays, it's getting better, but now with the increased cost that we have in some of these parts for the reasons of COVID and supply chain issues, this has driven a pretty good bit of cost into our system, more than I expected it to. There are things we can do here. Obviously, we could combine hardware root of trust and LTPI into one part. But ideally, I would like to go even further and if we could have BMC, LTPI, and hardware root of trust as one part. Obviously, that's the best case, and that could get us back to close to parity cost-wise with what we had previously. And we're talking to partners and seeing in general in the industry that's kind of the direction that folks are moving. There is work being done to try to combine these into 2 parts or 1 part. So I'm confident that we'll get there. The other thing that we've kind of run into that I feel will get better over time as well, since we were kind of first through here, we were hoping, and really we will all require that there's vendor agnostic designs here, so that you can have whatever vendor you want implementing your LTPI on the HPM, and you can have a different vendor on the BMC. Particularly for someone like us, as we look to provide, let's say, HPMs to other partners, we can pretty much guarantee that we're not going to have the same vendor that we choose to do our HPM LTPI implementation for, and whatever that partner's chosen for their DCSEM. We have found so far that not all LTPI implementations are created equal. We have had a lot of trouble here as we work with different vendors and try to mix and match. But having said that, we've also had real good success working with those partners to make sure that they are compatible, and we also see that trend where the LTPI implementation seems to be marching toward something where everyone will have the same implementation, or at least a compatible implementation. So this part should get better as well. So just some other considerations that I wanted to bring up. The DCSEM form factor, we would like to have options for vertical and horizontal HPM designs. This is obviously addressed in the current specifications, but there's some work to be done, and we're doing that work as we look at the next generation of HPM specifications, and as we work with DCSEM and 3.0 and future generations there. We're working to make sure that we have a solution for vertical and horizontal DCSEMs. But another area that we are primarily focused on cloud, but another area that we're kind of looking at now and seeing an issue with is we are looking to move into sort of what I call mid-edge with the DU and CU designs, and potentially even into far edge eventually. And the first thing you run into with those implementations is they require short depth chassis. And so some of them require very short depth chassis, 300 millimeters maybe, but even at 400, 450 millimeters, the problem that we see is with a coplanar, DCSEM, and HPM, it's impossible to get to those short depths. And so we'll need to address that, and we're working on that at the MHS level to at least start thinking about that and see what we can do there for solutions. And then lastly, for kind of issues that we've run into and things I wanted to bring up is PESTI. I like PESTI as a solution for board inventory and management. However, we have been in the past using VPD. For schedule reasons and risk mitigation, we chose to stick with VPD for now. However, we did fully implement PESTI in hardware. We kind of had to, since we're looking to provide building blocks to others. We want to be able to support PESTI, but even long term, I see the value to move to PESTI. It's not that much different than doing it in VPD. It's just something we chose not to do right now for, like I said, for risk mitigation reasons. But now that we have the hardware in place, we will continue with that in the future, and then we will, maybe next generation, but for sure by the second generation, or the generation after that, rather, for our products, we will have our firmware fully implementing PESTI versus VPD, and that can be done without any hardware changes here. So, turn it over to Dirk.
Dirk, if I may. Guys, if you allow us, we're going to step into your lunchtime just a bit, because this topic is really full. And I think that I owe them a little bit more. They've put a lot of good work into this. If that's okay with you guys, we spend maybe another 10 minutes after that.
Okay.
So take your time, please.
And I will try to hit the best points, because it is an exciting topic. So we heard from Paul on, what DCMHS is about, the building blocks and what we're trying to do. Then we heard from Rob about some of the challenges we face. When you start something new, obviously not everything's great, and we're working through those challenges, evolving those things and moving them to next generations. Now, this particular topic is, we coin it as shared infrastructure. And I don't know if anybody was at the Global Summit or watched some of those things, but some of the early thoughts process behind this was work that we had done with CMAC, and I think we presented a presentation similar to this topic with Sean Doobie from Dell and myself that talked about the ability to be able to put together shared infrastructure elements. Now, what do we mean when we say shared infrastructure? Well, essentially, when we started having these conversations, it was kind of almost comical that we were saying, well, you're building these chassis-based solutions, but whenever you look at these chassis-based solutions, these things are not common between each other. Remember, we're trying to build Lego blocks or building block approaches on how these systems come together. We were hearing from the participant companies that we have 12 different chassis and none of them even work together. They don't even talk simultaneously. So we said, well, this might be something we want to take a look at. So the intention behind what we're doing here is to build infrastructure or building blocks to be able to allow you to improve operability when you're building these chassis-based solutions, or these shared, as we call it, shared infrastructure solutions. So what was our focus when we started looking at shared infrastructure? Well, our focus was 4 key areas: shared power, shared management, shared input and output functionality, think CXL, PCI Express, and shared cooling. And our intention was to develop a series of specifications that allows us to be able to pull those elements essentially together in a common fashion, but still allow differentiation. So what do we mean when we talk about a shared infrastructure platform? Well, if you look at these systems, we've got 4 particular systems that's showcased here. And if we look at these 4 systems, you can see they're different in orientation. There's others. What we don't want to do is we don't want to define the platform per se. We don't want to build a full chassis, full infrastructure system, but what we want to define is how the things communicate with each other, how they're provisioned, how they're managed, how they're discovered. We would love to see those elements. And then, up to the point of defining the connectivity. Find a series of connectors that can create scale in the industry that drives the cost of these connectors down to make this something that everybody can take advantage of. You get data center scale everywhere. That's a beautiful proposition if you think about it. So when we look at this solution, how do we break and decompose the system? We started talking about a decomposition of the system, and the decomposition of the system really came down to a few key things. We looked at what is a shared infrastructure boundary. So what are you trying to manage? What are you trying to orchestrate? What are you trying to provision? What are you trying to control? Then from there, we had elements. Now, we define these as core elements and shared elements. In a core element, you have key things like the host or compute elements. You have peripherals, potentially acceleration capabilities that exist within these elements. Now, shared elements, these are things that these compute entities will be trying to realize. So if you guys have, I'm sure every one of you seen CXL presentations. This diagram looks very CXL-like, but the intention for it is that this is starting to realize some of those particular elements and how those things start to come about, is that these shared elements, shared memory, shared storage, pooled I/O, GPUs, accelerators, now you start to see those efficiencies starting to come to fruition. And as we start to evolve these specifications, there's a 0.3 revision out there, you could start to see some of our vision for how we're going to pull these pieces and these elements together. So, but these are the fundamental things. Now, what did we leave out? What we left out was essentially the fabric, because everybody's fabric is different. The common point of convergence was PCIe or CXL. That's where we found it, but there's dozens of fabrics out there. So for now, we left the fabric out of this definition because we didn't believe that that was something that everybody could converge on. So there's two key elements. There's a high-speed interconnect. You can think of this as PCIe, CXL in the solution. There's also the shared chassis infrastructure elements, which introduce your shared power, your shared cooling, and if you have a shared chassis manager, those solutions. But the high-speed interconnect piece of this is how you communicate within the system. In addition to that, we also have a notion of a management plane. Now, I'm going to explain in the next slide how those pieces come together. But when you look at the particular elements here, now in the management infrastructure, you need to be able to manage all the different elements that exist within the system. How does that come about? You have to have some level of aggregation that pulls all the elements together, as well as having direct interconnect. We're still working through what these things are, but the key thing that we're running into as we're working through the solution infrastructure is that if you look at that aggregator and you start thinking of in elements, notice I didn't say 8 elements or 4 elements, in elements. We're really trying to define an architecture that is truly expansible, because over time, technology gets better and better and better. These things are going to get smaller and smaller. If you define something that's bounded, you just run into a new architecture 3 years down the road. So that was another key goal. Where we end up at is trying to minimize signals. And if we look at the methodology of what we're trying to do, and it's kind of shown, and I wish I had a pointer, but we break out the management interface, the data slice interfaces, and the power interface. We see this as the 3 main connectivity options that's required to be driven into each element, be it shared or core. These are the 3 key things. And what we tried to do is we believe the management interface can be converged for all the entities that exist within the element. And we believe the power interface can be converged for all the interfaces that exist within the element. But notice the data slices are 0 through n. And we create those as independent entities on 16 lane boundaries in order to allow scalability to an N-type topology. So we're not trying to converge all these things and their interconnect together, and that's a really, really important point. Now, as I mentioned a second ago, the aggregation elements of this, when you start to look at all these signals, it starts to become complex. If you got 4 data slices coming from 8 different elements, trying to all drive into an aggregator, that's a lot of signals. So part of the effort is to find the optimal set of interfaces for both the management interface as well as the data slices to allow this stuff to converge on a solution space
that is really finite. It's really, really optimized to get the job done. So when we've talked to the players involved in DCMHS, and right now it is, from a silicon perspective, it is Intel, AMD, and Ampere. From a enterprise compute perspective, it's HP and Dell. And from a cloud perspective, it is Google, Meta, and Microsoft. Did I miss anybody? And then from a manufacturing perspective, it's Jabil. There's opportunities to contribute. We would love to have folks on board. You can contribute on the pieces that you like to contribute on. When you look at the specifications that we have, there is a wide breadth of specifications that the DCMHS has brought forward in a very short period of time, less than a year, honestly. Well, maybe a little over a year now, but, you know, this is, and it's not stopping. This is an evolution, and if you look at the momentum that's behind this, you know, from an industry scale perspective, it's absolutely phenomenal. I mean, this is I've been having fun walking around with Andy all week, Paul, sorry, and they see Intel and AMD walk up together, and they're like, hey, are you guys friends now? Well, we've been friends for a long time, but, you know, I think they're referring to Intel and AMD. But the reality is this is about making something better for the industry, you know, making something better for everybody involved. And it's not just the data center. It's for everybody. And I think if you start to look at the scale cost from, we mentioned the MPIC adoption and the MXIO adoption. People love the connectors that's been defined. They're looking at it in edge markets and various other things and saying, wow, these things are great, you know. We're looking at high-speed signal integrity. We're looking at, you know, where the world's going to, PCIe Gen 6 and PCIe Gen 7, and thinking about those things now to provision this architecture for the future. So the call to action here is, here's the specifications. If you want to join, that's the contact information. You know, if you feel like you have something to contribute, that's great. I tell you, each and every person in this room has something to contribute, and that's feedback. Even if you don't want to come in and participate in the meetings, read the specs. Let us know. We really take this seriously. We review these things that come in every week, you know, so please read the specs, look at it, and I hope you've enjoyed this presentation. Thank you all, and we'll get you out to lunch.
Thank you very much. As Dirk and others said,